structure of the density matrix is parameterized by mu, you can see that the left half of the system, left half of your chain, has a magnetization which is tanh mu, and the right half has like magnetization minus tanh. So there's a domain wall in between. Right? And what was shown in this paper is that if you look at, say, just a single spin and the expectation value, and you take the limit mu goes to infinity, mu goes to 0, this gives you a way to calculate spin-spin correlation functions at infinite temperature. And so, for instance, here you see beautiful data collapse with this exponent 2/3, which you would expect from KPZ. And not only that, they were able to calculate the spin-spin correlation functions and match it to the predictions from the slope-slope correlation functions at KPZ. So this is a really powerful conjecture, but it should surprise you a little bit because there's no noise in the Heisenberg model. It's a perfectly clean quantum system. So it's surprising, to say the least. Right. So since this conjecture, there were a lot of different efforts to experimentally verify it. So I've listed a few works here, but the one that I'm going to be focusing on today is this experiment from Manuel Bloch's group. So there they had two species Bose-Hubbard model, and in the limit of a single particle per site and large interactions, this reduces to a Heisenberg model. And you have a chain of 50 spins, and what was measured in the experiment is that if we start off in some domain wall state, we measure the spins or the excitations that are transferred from the left half to the right half of the system. So this is called a polarization transfer or the transfer of magnetization. And what they were able to show in this paper is that if I look at the polarization transfer, it obeys this as a function of time, it grows with this characteristic exponent, which is 1.5 sigmoid case. Alright. Now, just beyond the mean of polarization transfer, what they also looked at in this paper is the distribution itself. And in particular, they tried to characterize the skewness of this distribution. And interestingly, what they found that along times, this had a finite skewness, which is in consistency with the GUE Tracy widow. And therefore, this seemed to be good evidence for the KPZ conjecture. Alright. So you may wonder that, well, KPZ has been confirmed and everything, so why are we doing another experiment to look at it? Well, there's a fly in the ointment here. And the problem is that the KPZ conjecture, it relies on this mapping that the spin corresponds to my gradient of the height field itself. Okay? So you can immediately see that if I have a spin domain wall, this Heaviside theta function, it will map to some wedge initial state for the KPZ height field. Okay? And similarly for exactly at mu equals 0, you get something which is a stationary initial condition. So Hartman et al. And some intense numerical work in 2018, what they showed is that if you look at the height at the height field at the center of the chain that is related to the polarization transfer, that's actually characterized, the fluctuations of those are characterized by these corresponding distributions. And these distributions all have a fairly large skewness, right? But if I'm looking at spin transfer at infinite temperature in equilibrium, there's no distinction between left and right. Particles equally likely to move left as well as right. So the spin transfer, the polarization transfer distribution cannot have a finite skewness, right? So there's some inconsistency here, which is what we are seeking to explore. So in the experiment that we collaborated on with Google Quantum AI, what we were simulating is actually an XXZ model in the limit of the anisotropy parameter, delta going to 1. This just becomes the Heisenberg model. And what allows us to actually simulate this is a method of integrable trophization developed by Thomas Porzen, which allows you to develop a Fouquet circuit that implements dynamics, but preserves the integrability that we're interested in. So here's a chain of 46 qubits, and we applied high fidelity 2-qubit so-called FSIM gates that are parameterized with these angles theta and phi. So theta tells you about the hopping amplitude, and phi is the conditional phase that you pick up when two particles are next to each other. We don't worry too much about the gate details. This is what we implement. And here are some snapshots that I'm showing you for different values of mu. So when mu goes to infinity, you have a very sharp domain wall state, as you can see over here. And as you go to lower and lower mu, the distinction is not as sharp. And then we let the experiment run for some cycles. So here I'm showing up to like cycle 24 or something. And for each cycle, you can look at the distribution, the probability distribution, And so, for instance, here as a function of time, you can see that initially very few excitations have been transferred, so the distribution is very much to the left. And then as time progresses, it moves rightward and flattens out. Great. So what can we do with this information? The first thing that we look at is, of course, the mean and the variance. Right? So in the XXZ model, we know that depending on whether delta is less than 1, equal to 1, or greater than 1, we can have ballistic, super diffusive, or diffusive transport respectively. And when we plot the mean of the polarization transfer as a function of the cycle time, we do see that this confirms our expectations. And this is also reflected in the probability distribution, where you can see that, of course, ballistic is faster than diffusive. Right? So this particular plot is for a finite value of mu, which is set to 0.5. We want to study this now as a function of mu, because we're interested in the mu goes to 0 limit, which is where we are at infinite temperature and where the KBZ conjecture holds. Right? And so as we look at the case where delta equal to 1, both the mean and the variance scale with this characteristic KBZ exponent, so everything seems to be good here. However, as I've repeatedly mentioned, to characterize the full probability distribution, it's insufficient to look at just the mean and the variance, but we also need to look at the higher moments. So the first higher moment that we're looking at is the skewness. And as you can see, the skewness starts off at a large negative value, and then as time goes on, it tends to 0 as mu goes to 0. We can also look at the kurtosis of the distribution. This is experimental data, which is some scattered, but it agrees reasonably well with theory. And what we find is that there's a small negative kurtosis, which is minus 0.05. So if you remember the distributions and their respective skewness and kurtosis values that I showed you earlier, this seems to indicate that this is not governed by KBZ physics. Alright, so you might then ask a very fair question, which is that KBZ should hold only at time goes to infinity, mu goes to 0, so you're not really in those conditions experimentally, are you? So to get around that, what we did was we plotted the 0 crossing of the skewness, and we found that it scaled as this mu parameter to the power minus 1.5. And this actually motivated a scaling ansatz, which says that suppose I plot everything not as a function of time individually, but this combination, which is mu t to the 2/3, do we get a scaling collapse? And we should if there's really universality. Right? And for the skewness, we do see a scaling collapse. And this allows us to actually study various limits. Okay? So if you look at the left limit corresponds to taking mu goes to 0 first, and then t goes to infinity. And of course, because we're taking mu goes to 0 first, the skewness has to vanish, and hence it's not KBZ. If you look at the right limit, where t goes to infinity first, we know theoretically that the system has to cross over to diffusion on a time scale that goes with 1 over mu cubed. So if you have diffusion, that's, again, not KBZ. Then you might argue that, well, I keep my mu t to the 2/3 not at infinity or 0, but rather keep it fixed at some big value. What happens then? So in between, we see that, okay, this could be Tracy-Willem GUE, but if I look at the corresponding kurtosis at that point, it's again small and negative. So it's definitely not characterized by any of the usual distributions, Tracy-Willem or by grains, that we would expect for KBZ. So really the open question that I want to pose today is that what is the physics that produces this full counting statistic, this distribution function? And there have been a couple of models. So for instance, there's this nonlinear fluctuating hydrodynamic model of 2 coupled stochastic modes. It gets the skewness right, but it predicts a much larger kurtosis. Very interestingly, there was another totally classical Landau-Lifshitz model with some uniaxial anisotropy, and that seems to produce a kurtosis that is actually consistent with what we see in experiments. But again, the correspondence between that classical model and the spin chain is a little uncertain. Alright, so before concluding, I just want to point out an interesting caveat or development, which is that all of the experiments that we have talked about so far, to measure the full counting statistics, or the high distribution function, what you do is you prepare some number sharp initial state, and then you sample different number sharp initial states to get a distribution, and that's how you work with density matrices. But this means that you're never really preparing a terminal equilibrium state. And secondly, if you have noise, in the presence of noise, FCS measurement this way does really badly, and it scales exponentially poorly with the subsystem size, because you're very sensitive to decoherence. The number count is sensitive to decoherence deep inside each subsystem. Right? So in this theory paper down here, we actually proposed a way to get around this. And the trick there is to use an ancilla qubit. And in between each layer of your brickwork circuit, we apply a controlled phase gate with plus lambda and minus lambda on the ancilla. And while I will not get into the details, what essentially this does is that the ancilla now acts as a turnstile, where every time a particle passes through the cut across which you're measuring the polarization transfer, the ancilla picks up a phase. And then by reading out the phase at the end of your time cycle, you know how many particles have passed through. You can construct the moment generating function, and you can read off all the moments and compute the FCS. All right. So with that, I leave you with my take-home message, which is that if there is really a universality class in which the dynamics falls, we do not know what that is right now, but it definitely does not seem to be KBC. All right. So let me just thank my collaborators, Sarang at Princeton, and the group who run the IT. Thank you.
Thanks, Ryan, for the great talk. So, do we have any questions?
Yeah, you showed comparisons to simulations. And I was curious what kinds of effects you were incorporating in the simulations in particular. I was interested in whether the experiment has SU2 symmetry breaking effects, which for diffusion, and also.
Great. So that's a great question. So at any finite mu, you do have SU2 symmetry breaking in the experiment. Okay. So that is definitely the case, and so therefore at finite mu, even if your delta equals 1, you really do not expect superdiffusion. It's really a statement that in the mu goes to zero limit, that is when you expect superdiffusion. Now in the simulations, the simulation data that I showed, we tried a variety of things, including dephasing noise or amplitude damping noise. We tried a lot of different things, and it doesn't seem to matter too much, unless the noise is super strong, which does not seem to be the case.
Okay, I also have a quick question. So, why do you always look at this special initial state and not directly calculate the infinite temperature correlation function, like by state sampling, for example?
Yeah, you could. So this special initial state, it's a trick. Okay, it's a trick that if you prepare this domain-wide initial state and then take the limit mu goes to zero smoothly, that gives you your infinite temperature spin correlation function. So there could be a better way of doing it, but this is just a convenient form to be like so. Yeah.
Do we have any more questions? Okay, if not, let's thank Ryan again.